This is Chapter 6 from AS Maths Statistics. We are looking to continue to build upon discrete probability distributions today by introducing the binomial distribution. After completing this section, you should be able to understand the binomial distribution as a model and comment on its appropriateness. You should also be able to calculate individual probabilities for the binomial distribution. So to begin, we are going to link back to some of our pure content. Please can everybody pause the video now and attempt to expand a plus b to the power of 5. So hopefully everyone has now attempted to expand a plus b to the power of 5 using the binomial expansion. Just a quick recap, a binomial expression has two terms, so in this case we have a and b. And the binomial expansion allows you to expand powers of binomial expressions. So in this case, you should have found the following. I have just noted here the formula that will be given in your formula booklet during the exam. If you do need to revisit this topic, there are lots of examples alongside a detailed explanation in Chapter 12 of your Pure Notes booklet. So please do refer back to these if you need to. That being said, what I want us to do now is to consider whether there is a way to use the binomial theorem to find probabilities. So if everybody can just pause the video and have a think about that question. So hopefully everybody took some time to consider this question. The answer is yes. So if A and B add up to 1, then this type of expansion can be used to represent a probability distribution, and we're just going to touch slightly more on that on the next slide. Example 6.2.1. So considering the situation where a fair dice is rolled 5 times, what is the probability that you score a 4 on 3 occasions? So there are two possibilities for this experiment. Either we score a 4 or we don't score a 4, and that's for each roll of our dice. So these two possibilities can be written as a binomial, and that's where we have f plus n to the power of n, where f is us scoring a 4 and n is us not scoring a 4, and then we raise that to the power of n, where n is the number of times the dice is rolled, so in this case 5. So here we have f plus n to the power of 5 alongside its binomial expansion. As mentioned earlier, if we are considering an expression where a plus b, or f plus n in this case, is equal to 1, then the expansion can be used to represent a probability distribution. Here the probability of scoring a 4 on a fair dice is 1/6, and the probability of scoring anything but a 4 when rolling a fair dice is 5/6. These do sum to 1, and therefore the above expansion can be used to find probabilities for this particular scenario. When we look at the coefficients of the binomial expansion, these represent the number of possibilities, or combinations of 4s and not 4s in this case, represented by the exponents on f and t respectively. Considering f to the power of 5 then, this is a situation where we score 5 4s. And there is only one possible way of doing that, and that's by rolling a 4 on all 5 throws. This particular question then asks us to find the probability of scoring a 4 on 3 occasions. So we are interested in the probability associated with this expression here. So when we're looking at rolling a dice 5 times and scoring a 4 on 3 occasions, we've got 10 possible combinations. We need to multiply that by the probability of scoring a 4, because we've got a fair dice, that's just a 6. We're raising the 6 to the power of 3 because we want to score a 4 on 3 occasions, and then we just need to multiply that then by the probability of not scoring a 4, which is 5/6, again because we've got a fair dice, and then because we've got 3 4s and we're rolling the dice 5 times, then we must have had 2 occasions where we haven't rolled a 4. So when we work out that probability, everybody should find 125 over 3,888. So that's how we can use the binomial expansion to help us find probabilities. We will touch on this in the slides coming forward and we'll simplify it. Section 6.2, the binomial distribution. So when a random experiment only has 2 possible outcomes, we can define a random variable x, say, to represent the number of successes in n repeated trials of a binomial experiment. So what do we mean by that? If we had the experiment whereby we threw a fair coin 20 times and we were interested in the number of heads obtained, then we could define a random variable, x, say, to be the number of heads obtained in 20 repeated trials of a binomial experiment. It is important to recognise that we can't, however, set any random variable to have a binomial distribution. There are 4 conditions that must be met for a random variable to have a binomial distribution. One method of remembering these conditions is to use the acronym BINS. So looking at these 4 conditions in slightly more detail, B then stands for binary, and that's just referring to that there are exactly 2 outcomes to each trial, one being success and the other being failure, and this is often referred to as a Bernoulli trial. I then stands for independent, and this just references the fact that the trials need to be independent of each other. None of them should have any influence over another. N then stands for number, so the number of trials in the experiment has to be fixed, and the last condition then is the S for same. So when we're referring to same, we're looking at the probability of success in each trial being constant. If we go back to our example then of tossing a fair coin 20 times and run through the conditions to ensure our random variable can be defined by the binomial distribution. If we start with B, binary, so there are exactly 2 outcomes. So in our case, if we're looking at the number of heads being a success, then success would be the fact that we landed on a head, and failure would be landing on a tail. I then, for independent, the trials are independent of each other, because if I flip a fair coin, the first toss has no influence on the result of the second, the third, all the way up to the final 20th toss. And then for number, we have specified in this particular example that we are looking to toss our coin 20 times, so the number of trials in this experiment is fixed. And then finally, each trial does have the same probability of success, so we are talking about flipping a fair coin. So in this case, the probability of success is the probability that we would land on a head, and in each case that is a half. So there we can see that all 4 conditions have been met, and therefore x in our case can be described by a binomial distribution. So once we have checked our random variable meets the 4 required conditions to be modelled by the binomial distribution, we can let P be the probability of success in each trial of the experiment. Again, if we go back to our example of tossing a fair coin 20 times, if we are considering success to be landing on a head, then the probability of success P in this case is 0.5. The distribution of x then is written as x follows a binomial distribution with parameters n and p, where n is the number of trials and p is our probability of success. It is worth noting that when we're looking at the binomial distribution, we always refer to p as the probability of success and 1 minus p as the probability of failure. You might sometimes see 1 minus p written as q. Also then, this squiggly line here stands for has the distribution, and just a tiny bit on notation, this is called tilde. Then the probability mass function for the distribution of x is given as follows. So if we wanted to find the probability that x was exactly equal to a given value, the first thing we need to consider is the number of combinations. So this is our link back to binomial expansion and Pascal's triangle. So n choose x represents the number of ways of selecting x successful outcomes from n repeated trials. We then have that multiplied by p to the power of x, so remember p is the probability of success, and we need to raise that to the power of the number of successes that we are looking for, in this case x. We then have to multiply by 1 minus p to the power of n minus x. So if you remember that the probabilities of all outcomes of an event should add up to 1, then if we know that p is the probability of success, then 1 minus p has to be the probability of failure. and then that's to the power of n minus x. Notice that x plus n minus x gives us n. Because n is fixed, we have a fixed number of trials in our experiment, then if we know that we've got x successes, then we must have had n minus x failures. So moving back to our earlier example, if we let x be the number of heads obtained, then we said that x would follow a binomial distribution of 20 because we were flipping our coin 20 times, and the probability of success, so the probability of landing on a head, was just a half. If we wanted to find the probability that we landed on 4 heads, then we would use the following. So we could say that the probability that x was equal to 4 was equal to n choose x, so in this case I've got 20 choose 4. Our probability of success in this case is a half, and that needs to be raised to the power of 4 because that's how many successes that I'm looking for. And then we've got 1 minus p, so we've got the probability of failure, which again in our case is the probability of landing on a tail, which in this case is again a half. And then we would raise that to the power of n minus x. So because we know that we're flipping our coin 20 times, if I want my coin to land on a head 4 times, then that must mean that I've got 16 tails. If we then pop that into our calculator, we would be able to find our probability that x was equal to 4. And that's obviously a lot less time consuming than having to figure out every combination and all of the probabilities and then adding them together. So we're just going to move on to a couple of examples now. Example 6.2.2, a fair dice is rolled 5 times. What is the probability that you score a 4 on 3 occasions? So in this example, we need to define a suitable distribution to model the situation, and then we need to go on to justify our choice. So if we remember, when we are carrying out a number of trials in an experiment which has only 2 possible outcomes, we can define a random variable, x say, to represent the number of successes in n repeated trials of a binomial experiment. Here, we know that we have 5 trials because we're rolling a fair dice 5 times, and we have 2 possible outcomes: success when we score a 4 and failure when we don't score a 4. So if we let our random variable x, say, be the number of 4s rolled, then we can say that our random variable follows a binomial distribution where n is 5 and the probability of success is 1/6. So from there, please can everybody just pause the video and see if they can complete the reasoning behind why the binomial distribution is suitable. So for example, do we have a fixed number of trials? Yes or no? And then please can you just explain why? So hopefully everybody has attempted to justify the reasoning as to why the binomial distribution is a suitable model in this case. So if we just run through then, so the first one, do we have a fixed number of trials? Well, the answer to this one is yes, and that's because we know that the dice is thrown 5 times. Moving on then, are there 2 possible outcomes, success and failure? Well, again, in this case, if success is scoring a 4, then the other possible outcome is not scoring a 4, which would be failure. So there are 2 possible outcomes, either we roll a 4 or we don't roll a 4. Is there a fixed probability of success? Yes, there is, because the probability of rolling a 4 is a 6th, and that's the same every single time we roll our fair dice. And then finally, are the trials independent of each other? Yes, they are, because the first roll has no influence on the second has no influence on the third, etc. So here we can see that all 4 conditions do hold, and therefore we can say that the number of 4s rolled when we're considering we're rolling a fair dice 5 times can be modelled by a binomial distribution where n is 5 and p is a 6. So this won't always be the case. So for example, if we was looking at the trials are independent of each other and we had an experiment where we had a bag of counters and that bag of counters contains, say, 5 red counters and 3 blue counters, and we were looking at the probability of scoring 3 red counters, and every time we took a counter out of the bag we didn't replace it, the probability in that case would change each time, so there wouldn't be a fixed probability of success. And similarly, the trials wouldn't be independent of each other, because if I took a red counter out the first time, then that would have an impact on the second pick out of that bag. So whenever you're justifying a random variable and modelling it by a distribution, we just need to make sure, if we are looking at the binomial distribution, that we can justify that all 4 of these conditions hold. Example 6.2.3. Given that x follows a binomial distribution where n equals 5, so we've got 5 trials and the probability of success is 1/6, so p equals a sixth. The first part of this question asks us to find the probability that x is equal to 3. So to do this, we can use the formula below. So we want to find the probability that x is equal to 3. So to start off, we've got 5 choose 3. So remember, this represents the number of ways of selecting 3 successes in 5 trials. We then have p to the power of x, so in this case we've got 1/6, which is our probability of success. 3 is then the number of successes. We then have 1 minus p, which is our probability of failure. And that's then raised to the number of failures. So because we've got 5 trials and we know that we've got 3 successes, we must have had 2 failures. When you pop that into your calculator, you should get 0.0322. Please can everybody now pause the video and attempt parts B and C. So part B then asks us to find the probability that x is equal to 0. So this is very similar to part A, except in this case we want 0 successes and therefore we want 5 failures. So when you calculate that, you should get 0.402. It is just worth noting here that because we've got 5 choose 0, the number of combinations here is 1, and that's because there's only ever one possible way of achieving 5 failures, and that's to get a failure every single time. So that applies across the board when you're looking at n choose 0, and you also have exactly the same at the opposite end. So if we were looking for 5 choose 5, again we'd be looking for 5 successes, and the only way of achieving 5 successes is to achieve a success every single time. So again, there would only ever be one combination there. Moving on to part C then, we want to find the probability that x is greater than 1 but less than or equal to 3. So there are 2 possible values of x satisfying this condition, and that's when x equals 2 and when x is equal to 3. So we need to find the probabilities for both and add them together. When you do that, you should get a final answer of 0.193. The only thing I will say here is if you have used your value from part A, you just need to make sure that you haven't rounded too soon, because you don't want your final answer to include any rounding errors.